Hello, sir. This is my full counting circuit project. This is the first button input. The button input uses a pull-up resistor. And the pull-up resistor works by having resistor connected to ground and resistor connected to 9 volts, as you can see here. And the button set to ground. And both connect to the NAND chip. And when the button is clicked or held, the LED will turn off. And because when it is not held, the button will be on. This is because the NAND gate needs 2 low inputs to create a high and 2 high inputs to create a low. The low creates a ground for the LED to turn on. Next is the NAND gate oscillator. This circuit is an expansion on the previous circuit, which you can see here, where it basically looks the exact same, but it's a little bit different because it has a capacitor and a resistor. After the output of the NAND gate, so from here, which is the output, across down into these components, and basically the capacitor controls how long the oscillation lasts in the LED. So basically it's the exact same as the button input, just with this added on, because you still need 2 lows for a high and 2 highs for a low, but it just does it like kind of automatically, you could say. And yeah, that's the NAND gate oscillator. Next is the decade counter. The decade counter is the first section that you can see is quite different, as not everything is just over here. It expands the entire breadboard for this one. And you can see that there's 11 LEDs, where the final one here is green, and the 4017 chip, which is the main chip used in the circuit, is used to take the clock signal from the NAND gate, which is this gray wire, across, and splits the frequency into each LED. So it would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But the green LED is controlled by a different pin, or different type pin. Instead of just an output, it has divide by 10. So that makes it a little bit different, even though they all kind of do the same thing. Moving on to one of the final sections is decimal counting in binary. This circuit, of course, has the same premise as the one before, but instead of counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it counts binary. So it would go 1 or 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and so on, 0, 0, 1, 1, 0, 1, 0, 0, and all the way till all of them are filled. But since it counts in binary, it needs a new chip that specifically counts in binary, which is the 4010 chip. And this, well, you can also use the 4016 or 4516 chip, but it counts in hexadecimal, but that's not exactly what we want, so that's why it's better to use the 4510. And, you can see it here, collects the clock signal from the previous chip, basically just like stores what we already had, brings it over to this clock signal, and then you use it here for this circuit. But yeah, it's basically the same thing, just counts in binary. Finally, this is the final project on the breadboard, which uses the 4011 chip, which is the final chip, can see the 4510 here, so 4511. And the chip has outputs. Basically, every single pin is an output, so it goes A, B, C, D, E, F, G. And all these, A, B, C, D, E, F, G, connect to the corresponding pin in the 7-segment display. So there's like A, B, C, D, E, F, G, whatever. But basically, resistors and wires, the resistors connect from A to A, B to B, C to C, and so on. And the reason why you need the resistors is because the 7-segment display would blow if you didn't have resistors. So you kind of need them to keep your thing alive. And, you know, I use 4510 ohm resistors. If you use higher, it would still work, just it would be very dim, so you kind of wouldn't be able to see it, which is kind of what you need, but, yeah. Finally, we have the full PCB version of the circuit. You know, just turn it on, you can see 0. Click, counts down. Basically, same thing as the breadboard version, just, you know, it's all same components, all here, switches, everything. It just shows this a different way. You know, there's a battery underneath, inside of here. Screws hold this on. And yeah, this is the PCB version.